Hey guys, welcome to episode 2 of the mathematics series. This is Naive set theory. So we're going to start out with relations, then functions, and kind of establish what those are. And then we'll get into sets and then what you could do with sets, like operations and the relations on sets. So first of all, I'm going to say recall. So recall a predicate P is something that returns a true or false value, okay? So it returns a proposition. So in our example, in the last episode, we had P of X is true if and only if X is greater than 5. So P of X is defined to be, it means that X is greater than 5, okay? And then we had two different propositions. So we had P of 10 and P of 5. And so each of these are propositions. The first one has the value true, and the second one has the value false. Okay, so those are example from the last episode. So that's a predicate. So a relation R is a predicate of degree 2. Okay. So what this means is that R has two inputs. So we'd write something like R of X comma Y. Okay. And then this is the thing that's going to be true or false, okay? And so it depends on two different inputs or two different variables. So it has degree 2 right here. And also recall that we talked about the universe of discourse or the domain of discourse. And that's written like this. So R has some universe of discourse, and we're going to write degree 2. So we're going to write a 2 up here, meaning that has two inputs. If you don't want to use these numbers yet, because the cool thing that we're going to do next episode is define what these numbers mean, 1, 2, 3, 4, 5, the integers. You could write instead some kind of like meta-mathematical notation, like with some tally marks or something, and write 2 tally marks. But I'm just going to keep it like this. So it takes 2 inputs. Okay, so that is a relation. And one type of relation, 2.2 functions. One type of relation, one special type of relation is called a function, okay? And a function f is a relation, so it's a predicate of degree 2 is a relation such that, or that satisfies this axiom that I'm going to put down, okay? For all X, okay, and all Y, and all Z, okay, if f of X comma Y is true, and f of X comma Z is true, then Y equals Z. Okay. So this is saying that for some left input x, okay, if there are two different other inputs, y and z, that satisfy the predicate or satisfy the relation, the function f, then they must be the same. They must be equal, is what it's saying, okay? So another way of saying this is for all x, okay, if there exists some output or input or output, however you want to put it, however you want to say that, if there exists a y such that satisfies the function f for at x, then that output is unique. Okay, then there exists exactly one. This exclamation mark means there exists exactly one output f x comma y. Okay, so that is what a function is. So there are two ways to kind of say this, and the reason is because this quantifier here, this unique existential quantifier, is defined in terms of equality, and so it kind of breaks it down into a simpler form almost, because it compactifies the equality inside of itself. So those are two different ways to say what a function is, okay? If it has an output, then that output is unique, is kind of the idea. And the reason I say output is because when we have one of these, when we have this property here, where each input in the second slot is unique for each of the first inputs in the first slot, then we have this property that if we put something like f of x, comma, and I leave this blank here, if this can only be one thing, we already know what it is. And so I could put the output here, I could put y here, but it's not going to give us any new information, because if I say this is true, okay, and there's only one input that you could put in here, then we already know what that is. We know what that one thing is, and so this is in some sense giving us a new object. Okay, it's giving us y. So if we say this statement here, then this statement is basically telling us that y, it's telling us that y satisfies f of x comma y, you know. So it's almost outputting another object, in this case y. And the notation that we're going to use here is take out this comma, take out this empty space, and just write the output is going to be denoted f of x. Okay, is the output. So then we get things like f of x equals y. And that's solely because we have a unique output. If we had just a relation with many outputs, then we'd write something like r of x. Well, there might be many multiple like y's and z's that satisfy r of x comma y. So this could be true, and this could be true, and y and z could be different. They could be not equal, okay? So then when you say something like r of x, you're not giving us a specification of a single object. You're giving us many possible objects, like it could be y or z, that we want to talk about here. So maybe you could generalize this into like the image of that input, and then you could talk about like the set containing y and z, something like that, which is an idea. But the cool thing about functions is you know the exact output when you have one input. So that would be functions and relations. So now that we got that out of the way, let's talk about sets. So 2.3 sets. Okay. So I'm going to define it in a hand wavy intuitive kind of sense, because this is naive set theory. This episode is naive set theory. Next episode, I'm going to go into the axioms of formal set theory, and it's going to be a little more conceptually challenging. So I think it's good to have a basis of what you want sets to be, and then formalize it, as we do with all ideas in math. So a set is a well-defined collection. Okay. Collection. So I'm just going to use numbers as my examples. You could have, I'm going to use numbers and sets as my elements in all these cases, okay? Because there's no sense in using like colors and you know, that kind of thing, and people and names. These are just the basic math objects. Okay. So here I have a set of 5 numbers, 1, 2, 3, 4, 5. Okay. And the thing with sets is the only thing that matters, the only thing that the set actually sees is its elements. It doesn't count elements, so it doesn't care how many times the element appears, and it doesn't care what order they come in. So this notation that I have here with the curly brackets, that's like kind of the widely used set notation. But there are many different ways to represent it. So these representations are not unique, because this is equal to 2, 2, 4, 5, 1, 3, you know, because I'm repeating an element twice, and I rearranged all the orders. But the set doesn't care, because sets are determined based off of inclusion and exclusion. So all this set here sees, let's call the set A. Let's define it to be the set A. And all A sees is 5 pieces of information. It sees that 1 is an element of A, 2 is an element of A, 3, 4, and 5. This is all it sees, okay? So it doesn't see that 1 appears twice or 2 appears once or anything like that, or the order that they come in, because these are all just propositions. And remember, there's a conjunction in between each of these. And remember, a conjunction is commutative and associative, so you could rearrange them in any order, and it doesn't really matter. All this set A sees is 1 is an element, 2 is an element, 3 is an element, 4 is an element, and 5 is an element. An element. So an element is one of these members, is something that's contained inside the set. So like you have a bag, in a sense, a collection of things, and you look inside that bag, and the objects inside there are the elements, okay? So these ones are elements. Okay. And we use this little E-looking thing. It's the Greek letter epsilon, okay, which can be typefaced in a variety of ways. So epsilon is the relation between sets and elements, okay? So remember, a relation is a predicate of 2 variables, so, or 2 inputs. And so if you have a relation x comma y, here you got a predicate and 2 inputs, therefore R is a relation. So same thing here for epsilon. You have epsilon, and you have 2 inputs. In this case up here, in this first one, we have 1 comma A. But this is a little bit more confusing to write, because we have a predicate, and then we have 2 inputs, and it just looks nicer. and it saves 2 parentheses and a comma if we write it in the left-hand side way over here, which is sticking the predicate or the relation in the middle of the variables. So then we have x, r, y, and we do this all the time, namely the equality relation. Okay, we should be writing things like equals 2 comma 1 plus 1, right? 1 plus 1 equals 2. But instead we stick the equal sign in the middle and we write 2 equals 1 plus 1. Same thing for like less than, x is less than y. Okay, this is again a relation, so it takes in 2 inputs like this, but this is just the traditional notation that we use, and it saves space and it's a little more intuitive. So there's our first relation, by the way. So that would be sets, well-defined collections. And the last thing I'm going to say about sets is that you could also have sets as elements of sets. So you could have another set here. Something like that, right? So this is also a set, but its elements are sets. And in this case, its elements are subsets of this larger set because they're chosen from this larger set over here. Okay. One more notational thing is you could also have a set with no elements. So you could write it like this and just have nothing in it. Or an equally good way to say that, or to write that, equally good way to write that would be this, which we use a lot. It looks kind of nice. It's an O with a line through it, and that is the empty set. So empty set. Okay. Sweet. Okay. Let me just say something about set builder notation before we go on. So set is called set builder notation. And it pretty much does exactly that. Is you're able to kind of construct sets from a predicate, pretty much. So I'm going to use these brackets, these curly brackets again. I'm going to put a line here. Okay. And the way I'm going to write this is I want this to be equal to the even positive integers, okay? So positive, so start at 2, 4, 6, 8, dot, dot, dot. I'm going to write dot, dot, dot because it keeps on going. You could have infinite sets. And I want to define this in a different way. I don't want to write the dot, dot, dot. I don't want to have, I don't want somebody to be able to interpret what I'm saying. I want it to be more clear. So I'm going to say my set's going to contain elements. X is going to be my bound variable. And I'm going to have some predicate P for which X satisfies. So this predicate P is going to be my condition for the set. And then the set is going to be kind of a mirrored copy of the predicate P. Okay. I said in last videos that we have the class of predicates, and then we have the class of sets. And the class of sets is embedded in the class of predicates because it is a copy, right? It's a copy. So there's some other class, subclass of predicates that have some special conditions that is copied on the class of sets. And that's kind of what we see here is this this set builder notation. This is the set corresponding to the predicate P. Okay, it's essentially the predicate P. It's just it's a slightly different object, but it has the same information. Okay, because if you take some element or some object p of x, if p of x is true, that's equivalent to saying that x is an element of this set up here, you know. So they essentially have the same information. So we want a predicate p, and in this case, p of x is the predicate that x is positive and even. So x is greater than 0 and x is even. So x over 2 is an integer, let's say. That's one way of saying it, right? Positive integer. That is our predicate p of x. So that would be sets. We did relations, functions, sets. Let's go to some set relations. Okay, so 2.4. Set relations. Okay. So we already talked about one, which is epsilon, the element relation. And this has to do with inclusion in the set. So, for example, 2 is an element of 1, 2, 3. Okay. The other one that we also talked about is equality. Okay. And we said that two sets are equal if they have the same elements. And we said nothing about repetition or order. So, right? So, inclusion and equality. The last one is the subset relation, okay? And this is pretty intuitive. So, I'm going to do it by example. So, 1, 3, 5, 7 is a subset. And it's almost like less than or equal to sign. But it's instead of a sharp notation, it's a circular. That's what we use for sets. So 1, 3, 5, 7 is a subset of 1, 2, 3, 4, 5. Okay. So I have a larger set over here, and it includes all of the elements that are in this smaller set over here. So the smaller set is a subset of the larger set. That's what it means. Okay. So that would be set relations. And obviously you could reverse these, so you could have the, the reverse of the inclusion relation. The reverse of the equality relation is the same thing. And then you could have the reverse of the subset relation, which is the superset relation. And those work the same way. So that would be set relations. Last thing is set operations, okay? .5. Okay. So set operations. The first one is the union. Okay. So union of some family. Okay. So some set. In this case, it's going to be a set of sets. So its elements are going to be sets. This is how we denote it. Is going to be all the elements that appear at least once in each of its sets. So example, the union of this family here, 1, 2, 2, 3, 4, right? So I have these sets as elements. This is equal to this set here. 1, 2, 3, 4. So it is all the elements that appear at least once in each of the sets, okay? So there's a special, this is an operator, right? There's a special notation for when we take the union of a family of 2 sets. So, or I guess you could do it of any sets. So another way to write this, okay, is as an operation, okay? So this is another notational thing. And we could simply write 1, 2, small cup, 2, 3, 4, okay? And same thing if you had more elements, more sets, right? A larger family, is you could just put small cups in between each one and list them that way. And this eliminates a couple of the parentheses and a comma, similarly to how we do relations. We just stick it right in the middle. Okay. So the next one is intersection. And it's the upside down version of this. It's a cap and then the set that you want to talk about. Okay. So I'm going to use the same example, but I'm going to use intersection. So 1, 2, intersection, 2, 3, 4. Okay. This is defined to be the intersection of this family here. Okay. And this is equal to all the common elements between the sets, okay? So in this case, 2 is the only common element, so it's the set that contains 2. Okay? Okay, because 1 appears in this set here, in this element, but it doesn't appear in this one, so you can only take all the common elements that appear in every single element, every single set. Okay? Okay, there's 2 more that I want to look at. So these are very similar ones. I also want to look at difference. Okay. Which is in, actually, I'm going to write this in a new frame. Okay. So there's 2 more, which are actual operations. They're not operators on a family of sets. They have to be operations because of the way that they're defined. So the first one is difference. Okay. And this is written as some set backslash another set. Okay. And it could be read as the difference of A and B or A minus B. And then the one after that is the Cartesian product. Okay. So with the difference, okay. So if you have 2 different sets, let's say numbers going up to 5 minus, and then we take a few of these elements, and even elements that aren't in the set. So let's say 1, 4, 7, 10, or something, right? Like that. So you just have 2 different sets. And this is equal to all the elements that were in the first set that aren't in the second set. So 1 is in the first set, but it's not in the second set, so we're not going to include it. 2 is in the first set, but it's not in the second set, so we can't include it, okay? So what this operation is doing is it's taking out all of these elements from the first set, okay? So we're going to take out 1, take out 4, and that's about it, because if we can't take out 7 or 10 because they weren't even in the first set. So we're just going to end up with 2, 3, and 5 is our difference. Okay. The last operation that I want to look at is the Cartesian product, okay? So this is written as A times B, okay? So A times B. So I'm going to write down the definition of it. A times B is defined to be the set, and I'm going to use set builder notation, so of ordered pairs, A comma B, such that, and here's my predicate, A is an element of the big set A, and B is an element of the set B. Okay, so this second part here is my predicate, right? It's a proposition when I have inputs A, small a, and small b. And the first part here is just establishing the form of my elements and the bound variables, A and B. So A cross B is the set of all ordered pairs of A and B. So one example would be 1, 2, 3 times 10 and 20. Okay, so I have two different sets here, and I'm taking the Cartesian product. The product will be this set here, 1 comma 10, 2 comma 10, 3 10, 4 10. Oh, there's no 4 in here. 3 10, and then you could start over and do 1 20, 2 20, and 3 20. Okay, so these are the elements of the Cartesian product that we're taking here. It's the set of all ordered pairs. So when you're doing math, you know, in like algebra 1, you're doing math on the Cartesian plane, right, is what they call it. So you're doing math on R, the real numbers, multiplied with itself. Okay. Is the Cartesian plane of algebra 1, right? And we write it like this. So we write two different axes, right? The x and y axis. And what this really is you have a real axis, because this is a list of real numbers. You have 0 here, then you have 1, 2, 3, and you have all the numbers in between and negative numbers. So this is a set. This is a representation of the set of real numbers. And then you have another set of real numbers, which you represent vertically. Okay. And everything in this plane is an element of the Cartesian product, right? Something like 2 comma 2, right? The set of all ordered pairs. So that's the 4 different set operations I want to look at. And one thing I forgot to mention was that operations are functions. Okay, so this is why we started off with functions, is because they have exactly one output for every input. So you could write something like f of x is equal to something, because f is functional and f of x comma y is true, right, as a predicate. So all these operations are, for example, like the difference of a, the difference of a comma b is equal to some other set c, right? And so what this is actually saying is that the difference of A comma B comma C is true, right? So this right here is the difference is a predicate. It's a function on the first two inputs and then gives you that functional output. Same thing with Cartesian product. Comma B, comma C, right? All these are predicates of three variables. And you might say, wait, but then is it a relation? Because relations are predicates of two variables. And the answer is yes. It's just that the first variable or the first input is an ordered pair. Okay. Is this collective here. That's one way of putting it. So same thing for union and intersection. So that would be episode 2, Naive set theory. We looked at relations, functions really briefly, and then sets and what you could do with sets. So I'm going to go more into the axioms of set theory and the rigorous form of set theory, which is ZFC set theory, next episode. And so I'll catch you guys in the next one.